All right, we are at section 28.2, motion of a charged particle in a uniform magnetic field. Let's share the PowerPoint, and we're going to look at some conventions here. We're gonna use this quite often. Magnetic field. I'm looking at the um, right-hand side, A and B. Magnetic field lines coming out of the paper are indicated by dots representing the tips of arrows coming down or coming outward. So if you see little dots, you think of the points of the arrow. So in A, the magnetic field is coming out of the screen right at you. Now, magnetic field lines going into the paper are indicated by crosses representing the feathers of arrows going inward. So think of it's called the fletching. The fletching on the back of an arrow uh, for stability, think of it as going away from you. So you see the little X's. Think of the fletching on the back of an arrow. That indicates that the magnetic field is going uh, inward. Now we might end up using uh, the you know, the same for a velocity vector. In other words, just in general, if you see a point, it's coming out of the paper. If you see the cross, it's the fletching of an arrow going into the paper. So those are the conventions we'll use. You can just see from this, if you do, this is kind of contorting, but if you do the B field and the velocity vector, notice that the particle is negative, so the force is down the back of my hand. Where's my contort a little bit more? There's the B field, the vector is my thumb over here, so that the force is downward. Okay, let's look over here. Now, when you have a particle, uh, a positive particle, let's do the right-hand rule. Let's start on the right-hand side of this circle. The magnetic field is going into the screen. It's going, the velocity is up, so the vector, the force vector, is inward. Now let's move it around, and magnetic field is this way, the velocity vector is this way, so the force is inward. And if we go to the bottom, the magnetic field, the velocity, and the force is upward. And you can see that this particle that is traveling is trapped. It's basically has a centripetal force uh, caused by the magnetic field. You have a particle traveling in a magnetic field, so there's a force on it. So the uh, the force is equal to the magnetic force, and that's mass times acceleration. Well, what is we know that the force is QVB sine theta. Well, in this case, the theta is equal to 90. The sine of 90 is equal to 1, so it's just QVB. Sine theta equals 1. So the force is equal to QVB, but we know that the mass times the acceleration is a centripetal acceleration, so it's V squared over R. So R, if we solve, you can see the V on this side cancels with the V squared on this side, so that just leaves us with QB equals MV over R. Well, if we solve for R, uh, you end up with MV over QB. Now remember this equation. The radius is directly proportional to the mass and the velocity, and inversely proportional to the charge and the magnetic field. Now, if it's just a particle, the mass isn't going to change. And if it's a particle, the charge isn't going to change. If it's a proton, it's going to be 1.6 times 10 to the whatever it is, 19 minus 19 coulombs. So it's not going to change. So the mass and the charge aren't going to change. The only thing that's going to change is the velocity or the magnetic field. So whenever you have a fraction like this, if the velocity goes up, the radius is directly proportional to the velocity. So the velocity goes up, the radius goes up. If in the denominator, if it's inversely proportional, the radius is inversely proportional to the magnetic field. So the magnetic field goes up, the radius goes down. Remember that for the quick quizzes that are coming up. Okay, so omega, the angular velocity, is the tangential velocity divided by the radius, um, and that's equal to uh, QB over M. So you can figure out the angular velocity. Uh, all we did there was swap the we put the R in the denominator and put the MQB on the other side, inverted it. Um, so uh, the omega is found by the angular velocity is found by QB over M. All right, so the period is equal to 2 pi r divided by the velocity. In other words, the time it takes. In other words, you could say the velocity is equal to 2 pi r over the period. Well, you just swap the velocity and the period. The period becomes 2 pi r over uh, the velocity, which is equal to 2 pi over the angular velocity equals, we're using the omega equals QB over M. The period equals 2 pi M over QB, the charge times the magnetic field. All right, now let's do a quick quiz. You remember what I told you? A charged particle is moving perpendicular to a magnetic field in a circle with radius r. An identical particle enters the field with v perpendicular b, but with a higher speed than the first particle. Compared with the radius of the circle for the first particle, is the radius of the circular path for the particle smaller, larger, or equal in size? Well, let's go back to this. If v, what did it say? V is a higher speed than the first particle. So if v goes up, r has to go up. So it's larger. All right, now let's look at the next question. A charged particle is moving perpendicular to a magnetic field in a circle with radius r. The magnitude of the magnetic field is increased. Okay, let's go back to our equation. You increase the magnetic field, what happens to r? It goes down. It's inversely proportional. So the magnitude of the magnetic field is increased. Compare the radius of the new circular path of the first particle with the radius of its initial path. If the increase the magnetic field, the radius is going to get smaller. And sure enough, there's the answer, smaller. All right, let's see what we have here. The radius is equal to, I think this is really a repeat of some of the stuff that we've already seen. You can determine the radius by the mass of the particle times its velocity divided by its charge times the magnetic field. Omega is equal to, omega, the angular velocity, is equal to the tangential velocity divided by the radius, equals the charge times the magnetic field divided by the mass. Now the period is equal to 2 pi r over the velocity, which is equal to 2 pi over the angular velocity, which is 2 pi times the mass divided by the charge times the magnetic field. Now the velocity is the perpendicular velocity, and it's equal to Vy squared plus Vz squared. This is the velocity. If you're not quite, if you're at 90 degrees to the magnetic field, you're going to keep going in a circle. Well, if you're not quite 90, you're going to go in a helical path. So your Vy plus Vz, Vy squared plus Vz squared, take the uh, square root of that, and you get your velocity, which is the perpendicular velocity to the magnetic field. Let's see. Now we have some applications. This is a magnetic bottle. The magnetic force exerted on the particle near either end of the bottle has a component that causes the particle to spiral back toward the center. So this magnetic bottle is sort of a trap. You know, you can, if you have like two rings setting up a magnetic field, you can get this shape. You look up a magnetic bottle, you'll see some videos on the that show the particle. It's a complex path, and it goes around, and once it gets to the confined area on this side, it kind of reverses, and it just stays trapped, going back and forth into this uh, what they call a magnetic trap, a magnetic bottle. Okay, now here's the Van Allen radiation belts. Oops, wrong. Let's go back and look at, nope, still wrong. I don't follow my notes very well sometimes. Um, okay, you have the Van Allen belts. I showed you earlier on that we have the solar wind coming in, and so we have a lot of positive particles and not a lot of negative particles coming into this magnetic field. These, you can see that they show a lot of spirals. So these particles come in to the magnetic field, they get trapped, and it's what we call V cross B drift. Uh, they start spiraling, and they collide. Uh, they collide with some of the atoms in the atmosphere. So these particles, they get trapped by the magnetic field, and they end up going to either the poles, and they end up colliding with atoms in the atmosphere, and that causes our auroras. You have the aurora uh, borealis in the north, and you have the aurora australis in the south, and this is what causes them. You have these energetic particles coming from the sun, and sometimes coming from distant stars. They're called cosmic rays, but most of them, the majority of them, are from the solar wind coming from the sun. They enter into the Van Allen belts, get trapped by V cross B drift, and get spiraled into either one of the poles. If there's northern pole, you have aurora borealis. If it's at the southern pole, aurora australis, and that causes the aurora. That's one of my bucket list items, is to uh, see an aurora. I never have seen one. I've thrown a lot of items off my bucket list, but that's still one of them. Some of the others just don't become important anymore, right? All right, and I think that's it for this section. We're going to go to applications in the next chapter, but so we'll stop it here.